it's a pleasure to be here and to talk. I'm going to start my talk with a relatively simple statement that I hope will be understandable to everybody in the audience. So the statement concerns random matrices, and I'll just start, let's say, with the GUE. So this is a GUE random matrix. It's an Hermitian matrix with Gaussian matrix elements that are independent whenever they can be. So, and then I'm going to cut it in a slightly non-traditional way. I'm going to cut corners 1 by 1 here, 2 by 2, 3 by 3, and so on, at the top left. Then I'm going to look at the eigenvalues of these corners. So the eigenvalue of this one is just this entry. So it's one number. I'm going to put it on a real line. And then there are 2 eigenvalues for the 2 by 2 corner. I'm going to put them on the real line as well. And I will locate that real line right above the one that I started with. And I continue like that. This, you might notice that the eigenvalues, the way I draw them, are interlacing. And that's a simple linear algebraic fact. That's always true. Now I'm going to encode this picture by a height function in the following way. I'll just draw these broken lines to separate the plane into regions. And then you see the rightmost region will have the value 0. Then the next one will have the value 1, 1, 2, and so on. So what's the better way to say what I'm doing? I'm just taking a point on any of these lines, and then I'm counting the number of eigenvalues that are to the right of that point. Okay? And then I'm just forming a function in the half plane to extrapolate that. Okay? So the height function, the reason it's called height will be clear very soon, but for now it's just a step function that encodes my configuration. The basic result about random matrices, the Wigner semicircle law, says that if I now look at this picture from far, if I take enough number of levels, then what I'm going to see is that all the action is happening inside a certain parabola. And outside here, the height function is 0, and outside here, the height function just grows linearly. It's maximal possible. So if I want to know the fluctuations of this picture, then I should look inside the parabola. And there is a map, which is explicit. It's written here. It's the map that takes the inside of the parabola. I've chosen a particular coordinates here, which I didn't draw. But it's a map from the parabola onto the upper half plane. And that map, so you see how this picture gets distorted a little bit. So these horizontal lines become concentric circles and they get squished, right? So then we get a random function on the upper half plane. And then the statement I'm making is about the fluctuations of that function. So I take that random function, I subtract its mean. And then I want to know, what do I get? I get some random function again. To take the limit, what I do, I do the homotopy of the upper half plane. I just scale everything by a large parameter. And then the statement is that the fluctuations here will converge to what's known as the Gaussian free field, massless free field. In the upper half plane, I'm going to define the object if you've never seen it before on the next slide. Before I do that, I just wanted to clarify the status of the statement. So this is not a hard theorem to prove. Okay? The Gaussian fluctuations of random matrices have been studied for many years. These are results of the next order of difficulty from the semicircle law, the Wigner result. And so, for example, for a single random matrix without taking the corners, the fluctuations results can be interpreted as Zager strong limit theorem for Hankel determinants with the Gaussian weight. I'm not even sure where is the first source that states that the asymptotics. It certainly is in Kurt Johansson's paper from '98 that has a much more general result. Maybe it's in the literature from earlier on. The Gaussianity of the Gaussianity of the multi-level structure, so if I take corners, actually follows from, again, much more powerful results of Elise Guéhennet from more than 10 years back. So the only thing that sort of that I want to emphasize here is the structure of the free field. Okay, so free field is somehow a very canonical object in two-dimensional random processes, and not just two-dimensional, in any dimensional random processes. And that Gaussian free field structure, even though I just showed you how it arises, it remained unnoticed for a while. So it was noticed only recently. And the question that I basically want to address is why. So why is this Gaussian free field appears? You know, what leads to it? What is this change of variable here? Where is it coming from? And then I'll try to play out this theme, trying to sort of generalize it to natural things around the GUE matrices. So this holds also in greater generality. In particular, the usual moment method gives it for the Wigner matrices. And again, other generalizations I'll talk about a little later. So this is a quick slide on the Gaussian free field. So the two-dimensional Gaussian free field, that's what I will need, is a random generalized function. So the easiest way to define it is to take the random series. So here, these are the eigenfunctions of the Laplacian on a domain with a certain boundary conditions. I will only consider 0 boundary conditions. Now, these are the square roots of the eigenvalues. These are the independent standard Gaussians. And at every point of the domain, this series diverges. So the value at the point is not really defined. But if you smooth it out against anything, actually even against a measure concentrated on a curve, then this would be a well-defined normal random variable. So this is a simulation actually of a discrete Gaussian field that approximates the continuous one. At the limit, you see it's very rough, so it's believable. It shouldn't have values at the point. Now there are other definitions that sometimes are useful and that you might have seen. The Gaussian free field is a Gaussian process in the domain with the covariance given by the Green's function of the Laplace operator with the boundary conditions that you like. And also, if in terms of test functions, if you smooth out the Gaussian free field against the test function, then the covariance functional may be seen as the standard Dirichlet energy for the domain. The Gaussian free field is a conformally invariant object. So if you know it on some domain, you can just map the domain conformally, and then that goes into the Gaussian free field on the other domain. So this is, you might want to ask, what's the one-dimensional Gaussian free field? And the answer is the Brownian bridge. Okay, and so that really sort of shows that this is sort of a canonical object in a way. Okay, so going to the question as to why the Gaussian free field appears in the GUE matrices, I will start from something else. Now that something else is tiling models. Okay, so this is what it is. So I take a hexagon and I tile it with 3 types of rhombi drawn on the triangular lattice. Okay, the picture should be somehow self-explanatory. When you color these rhombi, there is also a clear 3-dimensional connotation of the picture. Hopefully it's clear that it's really a picture made of 1 by 1 by 1 cubes, right, put on top of each other. So, and then I'm going to look at all such that fit into the hexagon, and I will look at the uniform measure of them. So then if you scale things, so if you take the hexagon being large, then looking at the random thing will exhibit the structure. There is a certain law of large numbers that says everything is supported in some domain if you do the 2-dimensional projection. And then again, so there is a height function, which is a natural height function in 3 dimensions. Well, you might say there are several ways you can define the height function, counting height from different directions. It doesn't matter for the fluctuations. That's going to give the same answer. So take your favorite one. Then the inside of the unit disk here, in this example, that's where the action lives. Right? That's where things are not fixed. That inside of the disk, whatever radius it is here, it can be mapped to another disk. And that map may seem useless, but it's actually very important. That's the exact formula for that map. It's not terrible. You know, the thing is about the thing to know about this formula is that this is not a conformal map. Okay? It's a certain map from a disk to a disk. It changes the radius, but it's not a conformal map. And so under the image, the statement is that under the image, the height function here, the fluctuations of it also goes to the Gaussian free field, okay, in the disk. All right, now that wouldn't have been true if I did the same here, because the free field is not going to be a free field in this coordinate. It's going to be a Gaussian field, but it's not going to be a free field. Okay? So one needs really to change the conformal structure underneath to see this picture. So this phenomenon was first explained, not necessarily proved, but explained by Rick Kenyon, who showed how this should arise for general domains and general lattices. So this could be thought of as a dimer model on the hexagonal lattice, and one could do the same story, for example, for the square lattice, in which case one deals with domino tilings. And in general, the dimer models are related to the Castelline matrix, which is a modification of the incidence matrix for the underlying lattice. And the inverse Castelline matrix describes the whole picture completely, and that somehow is similar to the inverse of the Laplace operator. So one shouldn't really be surprised to see something like Green's function appearing. And so that logic was carried out by Rick in the situation when the tilings don't have problems near the boundary. Okay? Particularly, it's a very clean argument when one doesn't need to change the complex structure. That happens when the boundary conditions three-dimensionally are flat. And then the next level of difficulty is when the boundary conditions don't impose any frozen regions, so any parts with a solid color. And that can be sort of approached generically as well, but the generic methods didn't give any information so far, except for the intuition as to what happens with the frozen regions, in particular for the hexagon. And so this statement here was proved recently by Petrov by methods not unsimilar to the ones that were first used for the GUE before. And I'll talk about the connection a little later. I also want to say that this statement apparently is not just of interest by itself. In a very recent work of Fabio Toninelli with his student Lallier, what they did is they considered the heat bath dynamics on these tilings. So that's the dynamics where each box gets removed or added every time it can be removed or added. And so there was a big question, there's still a big question actually. They settled it in some case of the relaxation time of the dynamics like that. And so they considered that they solved that question for domains with the boundary conditions that don't enforce the facet, the frozen parts. And they used that result for the hexagon. So they used the hexagon to approximate the picture. And so this result actually has some applications for general domains as well. All right, so now what's the corollary? What's the connection between the two things that I showed? So I think it's best phrased by the general principle of Okunkov and Reshetikhin, who stated it a few years ago, and they say approximately the following. That if I look at the tilings by these rhombi, again, it can be carried over to other lattices. Let me stick with this one. Then you might observe some frozen parts, and then there will be a limit shape. And so if you look at the point where the limit shape touches the border, right? So something like that. Then near that tangency point, you can see that the geometry of tilings needs to be similar to the random matrix picture. So at the very bottom row, there will be exactly one rhombus of sort of vertical shape. And then on the next level, there will be two, and then three, and they will interlace. And so the principle is that when you scale things here properly, in the limit, what you will observe is the random matrix process. Okay? So at finite distance from the border, near the tangency point, you should be observing the random matrix thing. Now, why is that happening? So there is a hand-wavy explanation that says the following. If you're looking at the uniform measure on tilings, then it has something that may be called the Gibbs property, which is if you freeze the tiling, for example, above a certain level, then the conditional distribution on what happens below is uniform. And so if you then look at the real triangular arrays with interlacing condition that have such Gibbs property, actually all such probability measures can be classified, and that has been done by Chansky and Vershi completely. And then that's an infinite dimensional family, but somehow the only measure from that family that fits the picture is the GUE submatrices measure. Okay, so that's a possible explanation as to why one should be expecting this GUE minus process. And this Gibbs philosophy is actually quite useful. And so, for example, quite recently, Vadim Gorin used it to prove that the GUE submatrices process also arises in the 6-vertex model, or in alternating sign matrices, which is a harder model to study than random matrices somehow, well, than some random matrices in any case, because it's a not determinantal object, and in general it's difficult to access. Okay, so there is a sure.
If you do the same construction for GOE,
yes,
what happens?
So there is no I cannot give an explanation like that for GOE. So the conditional.
You would have a height model.
Yes. So the GOE will also converge to the Gaussian free field. That's not hard to show. But I cannot attach a tiling explanation to explain why that has happened. But the method of moments gives it for GOE as well. No problem. Okay. And the problem with GOE is that the conditional distribution, if you fix the top row, is not going to be uniform. And so it's going to actually have quite a bit of interaction between the particles. And so giving this sort of simple-minded uniform type explanation would be difficult. Okay. So a second explanation is more to, well, it may appeal to some, and it also uses a pretty word of semiclassical limit. If one looks at this, so I'll go through this rather quickly. If you're familiar with this, then I'm happy. If you're not, you can just skip that slide. If one looks at the Schur polynomials, which are characters of the irreducible representations of unitary groups, then these Schur polynomials have something called branching relation, or that solves the problem of restricting irreducible representations of unitary groups to smaller unitary groups. And so formally, these polynomials, if one substitutes the last variable to be 1, they decompose on polynomials with smaller indices, with smaller number of indices in a certain way. That way involves interlacing, and so that branching relation can be pictorially drawn as two interlacing integral point configurations that can be linked to tilings immediately. So if one does the restriction from the unitary group of any size all the way down to the unitary group of order 1, then this can be encoded by tiling of a certain of a polygon. And the polygon, the boundary condition on top, relates to the reducible representation of the larger group one starts with. And then there is a general principle in representation theory that says that large representations of a group are related to the group invariant measures on the Lie algebra, actually in the dual Lie algebra. That comes originally from the philosophy of the orbit method, but can be looked at in different ways. It has the name of the semiclassical limit, and so the representation theory of the unitary groups at large scale, which means blowing up this polygon, should converge to unitarily invariant measures on Hermitian matrices, and that's what we are seeing. Now, it's sort of important here that this semiclassical limit, it only works for finite size groups. Okay, if I go to groups whose size grows sort of comparably to the size of the representations, the principle fails. You need to keep the group finite and take the representation very large. Okay, so that's a second possible explanation as to why tilings and random matrices should be related. Okay, so now what I will try to do, so I stated my basic result. The height function converges to the Gaussian free field. And now I will try to explore the territory a little bit. I will try putting extra structures on my problem and seeing what comes out at the Gaussian free field side. Okay, and trying to sort of make sense out of it. So the first thing that is probably natural to do to random matrix ensemble, and very useful from many points of view, is to add the dynamics. In the case of random matrices, there is a canonical way of doing that called Dyson-Brownian motion. And again, going back to my original example of GUE, that just means that my matrix elements start, instead of being just normal random variables, they start executing independent Brownian motions. I'll do the stationary variant, so that means that they execute in stationary Ornstein and Lundberg processes. So then I can do the same thing. I can do the height function, then map it again to the upper half plane, which is the good conformal coordinate as I know. And now I'm getting a three-dimensional fluctuation field, and I want to know what it is. Essentially, same methods tell me that it's again a Gaussian object. It's a Gaussian three-dimensional field now. Can I call it something? Can I call it a free three-dimensional? No, it turns out that I don't know what to call it, but I can write the covariance matrix. Okay, so this is the covariance kernel that's written. If you remove these blue terms here, then what you read actually is the Green's function for the Laplace on half plane with zero boundary conditions, and so this would be just the covariance of the free field. But then you get the shift dependent on time. It's a pretty simple answer, and so there are many sections of this three-dimensional field that are actually Gaussian free fields. But the whole field itself, I don't quite know how to describe in invariant terms. I would like to say that this is related to this differential operator, so I can't do that. This is the best description that I can give. But it's not such a terrible description. The covariance kernel is pretty simple. Okay. So now let me go to the tiling picture and ask myself, fine, how can I put the time dynamics onto the tiling picture? Okay. Is there a natural way of doing that? Now, there are some possibilities, and in particular, there is a family of Markov dynamics that we happen to know how to analyze. So I'll give you an example of what one of them is, and then I will tell you what happens to the fluctuation field. Okay, and then we can compare to the random matrices whether the correspondence is still there or not. So this, I will take the simplest possible model. I could have worked with hexagons as well. I will take actually the limit of the hexagons where they get very large, and the sides grow in a specific fashion. There is a new parameter t appearing in the model, and I will look in the neighborhood of one vertex of the hexagon. So this will be a measure on tilings in the sector of the plane. And so this parameter t, actually, that is the parameter of that measure, should be thought of as time. And so this measure will be grown from t equal to 0, which is just densely packed tiling, to this one. And I will try to explain very quickly how the growth happens. Okay? So this is the initial condition. It's empty. This is the three-dimensional picture that I'm hoping you can imagine from this flat representation. And so to explain the dynamics, I will put particles in the midpoints of the vertical lozenges. Okay. So this wall here is pictured by this piece of the flat picture, and then the floor here is pictured by that part. So I'm hoping that you're seeing the picture. And so now these particles will start moving in some fashion, and then I will say what the three-dimensional interpretation is as well. So in order to explain how the particles start evolving in time, I imagine that there is a hierarchy on particles. So the particles on the bottom is the one that's most important. It will just do the random walk and won't care about anybody else on top. And then the next two are also important, but they will depend on this one, and so on. And then the dynamics works in the following way. Every particle has its own clock, and it tries, when the clock rings, it tries to jump to the right by 1. So that lozenge, this clock rings. This is my initial condition. This will be the first clock to ring. And this rhombus will try to jump to the right by 1 location. And sometimes that jump can be done, but sometimes that jump will come into contradiction with the interlacing structure. So my picture will get messed up if I just try moving these things. And so the rule to resolve these contradictions is the following, that if the particle, when it jumps, contradicts with somebody lower, then that jump is forbidden, because lower particles are more important. And if it contradicts with somebody on top, then that top particle will also get moved. So for example, if this one moves, then it pushes over that one, and that pushes over that one, and so on. So three-dimensionally, if you look at that picture, and again imagine that this is a corner of this form, then this corresponds to the dynamics of adding all possible one by something sticks into the picture so that there are no overhangs in the picture. And you can see that here there is this stick being put inside. Okay? Now this is a particular dynamics. And again, the reason I'm considering is because I know of certain good properties of this dynamics. And maybe this is not the most natural one, but at least it's not unnatural to be considered. In fact, so I'll just show how this evolves. So this is the type of the dynamics. It's an affine transformed picture, but hopefully you see that there is something going on there. And so again, the question that I will want to know is that at large time, I know somehow from before that at fixed time I will see the Gaussian free field as fluctuations, and I will want to know how these fluctuations change over time, and whether I will really see the same three-dimensional Gaussian field as the one that I saw in random matrices, where I had a different dynamics. Okay. All right, so let me go back there. Just a quick note. So this dynamics, I like it. I like talking about it. You may have seen it before. It relates to the 1 + 1 dimensional KPZ, because the leftmost particles here perform the projection to them is Markovian, and they perform TASEP. The projection on the rightmost particles is also Markovian, and it's also a 1 + 1 dimensional KPZ model. Maybe most importantly is that on each horizontal row, it turns out that the dynamics is also Markovian, and at large times it's the same as the one-row dynamics for the Dyson's Brownian motion. So this model at least has something in common with the random matrices, and at least on the single row level, the fluctuations should be same as in random matrix picture. Okay. So this is just a list of properties of this model. So as one should expect, at large times there is a limit shape that develops. That's a smooth limit shape. That limit shape changes with time. And the way it changes is according to a PDE. It's a fairly simple first order PDE. I didn't write that F explicitly. Well, it's not going to tell you much. What is important to me now is that this PDE can be solved by characteristics, and those characteristics are actually straight lines. And you can predict the limit shape by just doing that. Speaking of universality class, the model lives in the KPZ universality class, but it's the anisotropic KPZ. If you're familiar with the KPZ, the quadratic form here has a plus and a minus, but again, I'm not going to talk about that much. So the fluctuations, if you just pierce the picture with a needle, then the fluctuations at every single point are logarithmic in time. But if you want to consider several points, so you pierce the picture at several points, then there is again a height function that comes from the three-dimensional connotation, and you want to know the joint distribution of fluctuation at several points, and that fluctuation structure is the Gaussian free field structure. Okay, so at least at fixed time, we're back to the Gaussian free field picture. The big question is, to me at the moment, is what will be the time-dependent fluctuation structure? So here, the only partial results are known, but let me tell you what I think is happening. And it's confirmed by certain numerical simulations anyway. So what is happening is that the fluctuation field, the three-dimensional fluctuation field, essentially is described by a two-dimensional one. So what happens that if you want to know the fluctuations at time 2t, then what you need to do is to look at the fluctuations at time t and move them to the time 2t. And how do you move them? Well, the way you move them is along the characteristics that describe the growth of the limit shape. Okay. So this is conjectural. As I said, it's confirmed. It's confirmed by numerics. It's also confirmed by the following statement. That so what this picture is showing. So this is supposed to show the limit shape at time t1. This is the limit shape at time t2. So there is a fluctuation field here. There is a fluctuation field here. And what I'm saying is that the field here is just this one moved along these rays. Okay. So what we can prove is actually we can take certain surfaces that are not quite fixed time surfaces, but they should be somewhat close to them. And then if I cut this picture by a surface that's sort of space-like, then the field on that surface will coincide with the one on fixed time one moved along those characteristics. Right? So if I could prove something like that for any section, then I would prove the structure that I want. But for now, I need to settle with what I have. Now, if that conjecture that I'm trying to explain is valid, then this asymptotics will be different from the Brownian motion asymptotics. It's a different three-dimensional field structure than the Brownian motion structure. Now, do they agree at all? Can one reconcile the two pictures? The answer is probably yes. And so the analog of the Dyson-Brownian motion on the level of tilings is something that's not quite visible to the classical probability. This is actually a quantum random walk, which in representation theoretic terms amounts to tensor multiplying representations with a fixed one several times. Its projection to the tilings is going to be non-Markovian. But if one does things properly in terms of quantum probability, then one can see that the two things match. And that's the work of Jeff Kwon that is currently in progress. On the other hand, if I take the dynamics that I describe on tilings and try to ask what's the random matrix analog of that dynamics, right? So then I can't explain the answer in terms of random matrices, but I can explain the answer in terms of their spectra. So in terms of their spectra, that object is known as Warren's process. And I will explain what it is in the simplest non-trivial situation when we just have three particles, one on level 1 and two on level 2. So this one is just going to do Brownian motion, and these two are going to do independent Brownian motions that reflect themselves off the first Brownian motion. So that reflection of the first one guarantees that the non-interlacing happens at every moment. This object is not what one gets from Dyson-Brownian motion, but that's the one that corresponds to the tiling dynamics. And so its fluctuation structure should be the same as I described with the characteristics and the field being transported along the characteristics. Okay. So that's my first attempt to see what happens beyond the GUE. Now I will do two more. So I will do two more variations, two more extensions. Okay. So the next one that I will do may not. Well, let me just explain what it is, and you'd be the judge whether it's a natural thing to do or not. So what I will do, I will again start. So this is my original picture. This is my random matrix, height function, parabola, and then the new conformal structure. And so what I will do now, I will take a certain sequence of natural numbers, and I will take from my original matrix only rows and columns that have numbers in that sequence. Okay? So think, for example, of even numbers. I just take even rows and columns. And so if my matrix was a Wigner matrix, so the matrix elements were independent, then if I cut rows and columns, it's still a Wigner matrix. Right? And so with that matrix, I can play the same game. I can take the submatrices 1 by 1, 2 by 2, 3 by 3, and so on. And so that will give me the Gaussian free field structure, just because it's exactly the same as the one that I started with. So picking different subsequences gives me different free fields. How do these fields talk to each other? It's quite clear they can't be independent, right? If I take the full matrix and I take the matrix with even rows and columns, they have a lot in common. They shouldn't just be independent. Okay? And so the answer is below. The answer is that the joint behavior of all these Gaussian free fields is a Gaussian process. It's a huge Gaussian process. It's parameterized by, so I get the upper half plane for each sequence. But then I also have to have the space of sequences, which is a huge space. Now, I will assume that my sequences that my sequences are regular with respect to each other, which is the following. That if I take two sequences and if I take stretches of prescribed length of the first sequence and the second sequence, I take the intersection, then that intersection should behave in a predictable way. For example, if I take even numbers and all numbers, then I know the size of any intersection of that size. So I need the regular asymptotic behavior of such intersections. It's still a huge set of sequences. Yeah, pretty much anything you can come up with that doesn't involve some sort of an irrational going around. Well, actually, yeah, well, OK. If you don't go into arithmetic, then you're probably pretty much fine. Anyway, so this is the answer for the covariance kernel. Okay? You see that so this is the function that measures the intersection of two sequences I and j. And the zero case is when all sequences are just natural numbers, and then this is just the minimal value of absolute value of z squared, absolute value of w squared. And then it's just the Green's function for the Laplace operator. So this is some sort of an extension of the Gaussian free field, and it's a way to combine many Gaussian free fields together. It's a non-trivial answer, and I'd love to have a conceptual meaning for that answer. I don't have it. Okay? But the formula is reasonable. Okay. All right, so as I said, you may decide for yourself whether this is a natural thing to do or not a natural thing to do. The origin for that setting of the problem actually came from the tiling model. So for the tiling model, picking submatrices sort of doesn't make sense because what's the row number and the column number? But it can be interpreted in a representation theoretic way. And again, you can skip the slide if you feel like it. So I mentioned that tilings of this form, they come from taking a representation and restricting it to smaller unitary groups. Right? Now, what's more, not only I have to do that, but I have to take the maximal commutative subalgebra in the algebra of operators generated by these groups. And then on that subalgebra, there is a trace of representation. And so by abstract theorem, if I have a commutative subalgebra with a trace, it needs to be the algebra of functions on the spectrum, on something, with a measure in it. And so in this for the particular choice of something called Gelfand-Setlin subalgebra that's generated by centers of the universal enveloping algebras here, the spectrum will turn out to be tilings like that with the uniform measure on them. Okay? So that sort of lifts me into the setting of non-commutative probability. And then I could ask, OK, fine. So I have this huge representation. And then I restricted it to a commutative subalgebra. That's a rather drastic operation. The representation is very large. I'm restricting it to a very small subalgebra. Can I say something if I restrict it to a different subalgebra? Maybe non-commutative subalgebra and so on. And so the best I could do so far was to restrict it to similar chains where my unitary groups inside the large group are chosen differently. I start with a unitary group rotating a single vector, or two basis vectors, or three basis vectors, and so on. And so such chain, again, gives me a Gaussian free field by the same reasoning. The two, one with the canonical ordering, or with the non-canonical ordering, now they won't commute. So they don't, these subalgebras won't commute, so they don't form a classical probabilistic space, but they form a non-commutative probabilistic space in the sense that the operators have trace on them. You can multiply them and take trace of what you get. And so the question of the asymptotics still makes sense. And so the asymptotics that one gets is, well, this one. So the asymptotics ends up being commutative but non-trivial. And the original idea was somehow to try to go beyond the curse of the commutative subalgebra. Take large representation and try to understand what happens to the operators when you go beyond the commutative subalgebra. And so originally it wasn't actually clear that when you take two non-commuting subalgebras, the answer will lie in the world of classical probability. But in this particular sense, it ended up being correct. OK. So that ends up my second story on trying to deviate from the GUE. Okay. So now I also have the third story, which will be the final one. And that's another deformation of GUE. It's known as the beta ensembles. So the GUE, when projected to the eigenvalues, as I'm sure all people probably in this room know, has the density of measure, which is the van der Monde determinant squared times the Gaussian weight. Well, it's not the Gaussian weight here, but you can imagine the Gaussian weight. Now the beta ensembles, they put the beta here instead of 2. They were introduced by Dyson, as far as I know, in order to study the GUE things from the point of view of log gas, from the statistical mechanical point of view. For the log gas, this beta corresponds to the inverse temperature. And so what I will do, I will take one ensemble like that. I'll start with the Jacobi weight. I need a classical weight here. I can't do anything with a non-classical one. And so the Jacobi is the most general one, so I'll take it. Now what I want to do, I want to tell you a story similar to the one that I told you before. Now the first question that I run into is, what is the analog of taking submatrices? 1 by 1, 2 by 2, 3 by 3, and so on. And it's completely unclear, because for general beta, there is a matrix model, the tridiagonal matrix model by Edelman and Dumitriou, but that model doesn't give anything meaningful if you start cutting corners out of it. It just doesn't have enough randomness to produce a proper two-dimensional object. So one needs something else. Okay. There is something else, and I'll try to explain why there is something else. There is something canonical that extends the n-particle beta Jacobi ensemble to many levels. This is just a formula. Okay, I'm not going to use that formula in any way. What I wanted to show is that this formula, so this is the formula that has the product over levels, and so the pieces of the formula are the van der Monde-like term to some power on each level, and then there are cross terms between different levels also raised to some power. So on each level, this is actually a beta ensemble. This is the van der Monde to the power beta. That's here is 2 theta, and then these are some Jacobi parameters that one takes. Now, why is so the ensemble is a little bit unusual, or not that it doesn't look like GUE immediately. What it has the growing number of particles up to some level, and then starting from some level, that number of particles stabilizes. Actually, what happens is that there are extra particles sitting at 1, and they must be there, and they accumulate there, but they're not interesting, so I'm not drawing them. Okay? Now, what is this formula, and where is it coming from? So there are two sources that are easy to explain. One is that if one goes back to the problem of evaluating the partition function for the beta, for the beta log S, that's known as Selberg integrals. Right? There are many different proofs of Selberg integrals, and one of these proofs goes through something called Dixon-Anderson integral. So that's the integral that allows one to reduce the number of variables in the beta ensemble from n to n minus 1. That goes back to a formula of Dixon in 1905. So this is very much a special functions argument that extends the remarkable integrals of Selberg to the multi-level situation. Okay, and this density here is consistent with these integrals. Okay? Now, leaving that aside, so this is sort of a formula explanation. Now, leaving that aside, a more invariant explanation is the following: that where do beta ensembles come from? So for beta equal 1, 2, and 4, these ensembles are much like GUE originally, come from the spectral measures for the Riemannian symmetric spaces. Not necessarily Hermitian matrices with a unitary group acting on them, but some other Riemannian symmetric spaces with some special values of these parameters P and Q. Each symmetric space will have beta, which is 1, 2, and 4, or 4, and then some values here and here. And so one can try taking these 1, 2, and 4 points and extrapolate them. And so one can do that, and the extrapolation will look like that. Okay, that's another possibility. So that's an example of how Jacobi ensemble comes out from the spectra. If you take X and Y being Gaussian matrices, then if you form a matrix like that and look at its spectrum, then in general these two matrices can be rectangular, and then moving the size of one of these matrices will actually produce the multi-level structure of this form. Okay. There is also actually having the convenience of Alan Edelman being in the same department. I know that Alan Edelman actually has also a construction of what would be a matrix model for this thing, a general beta matrix model. It wouldn't be a tridiagonal one. It would be the one involving full matrices, except for these full matrices would consist of something that he calls ghosts. And so this is a, well, I won't go into that. You can ask Alan. But in any case, this is something he's capable of putting on the computer and checking the results that I'm about to state to like 4th digit for arbitrary beta, which I think is a pretty good proof that what he does is, well, must be close to being correct. I'm not sure if there is a proof there, but in any case, the agreement that we saw was pretty amazing. Okay, so what's the result? The result is in the same spirit. So this is my array of eigenvalues. I construct the height function in exactly the same fashion. And then when I scale the whole thing, my liquid region, so the region in which the action happens, is no longer going to be a parabola. It's going to be some algebraic curve, which has a specific shape. So this is the point where, this is the line where the number of eigenvalues reaches the maximum, and then they start, well, you can see from here, right? So this right border goes to the right and then back down. And then again, there is a map to the upper half plane. So that map is not too difficult, but it's not obvious either. So it takes this line to the vertical line, and then horizontal line like that go to certain circles. They're no longer concentric circles, but they are explicit circles. And then again, as things get large, the limiting fluctuations here are going to be described by the two-dimensional Gaussian free field. Okay? Now, in this situation, I don't know of any a priori explanation of why it should be the two-dimensional Gaussian free field. If for GUE I can come up with the representation theoretic story, quasi-classical limit, whatever, here I don't know. Still, the result gives the same universal object. So this result certainly has been approached from different angles by different people. So first of all, Kurt Johansson has a brilliant paper where he proves the Gaussian fluctuations with an explicit covariance structure on a fixed line. Well, he worked with the Gaussian case and more generally actually with convex potentials. Herbert Spohn probably was the first to say the words Gaussian free field in relation to random matrices. What he considered was the Dyson circular ensemble with arbitrary beta and with the natural evolution on it, and seeing the Gaussian free field there. The difference between the cylinder case or the circular ensemble with time is that this is sort of the flat case. In that case, the conformal structure that comes to you with the problem, so just the product of the time times the circles, the cylinder conformal structure is the correct conformal structure. You don't need to change it to see the Gaussian free field. It's already there. It's not quite hidden. Okay, but still, it's a wonderful result that I wanted to mention. Then there are works that consider the Dyson-Brownian motion on the real line as well, and computed the Gaussian behavior and the covariant structure. But again, the Gaussian free field underneath was not noticed, probably because just the authors weren't looking. And then Dumitru and Paquette can do the one-level result. And then, as I said, Alan has conjectural matrix models for arbitrary beta that work. Now, this last piece, the general beta piece, is probably the deepest result among all that I stated. And the way that it's proved is through the formalism of something called McDonald processes, which is a rather powerful algebraic mechanism of analyzing large time behavior of different probabilistic systems. And maybe I should have given the talk on McDonald processes instead. My excuse for not doing that is that I spoke about them in this room a few weeks ago, and some of you may have heard that. My second excuse is that last week we posted in a introductory survey article on the archive that explains, I think, a rather soft and natural way to enter McDonald processes. And so if you're curious, I think this is something that should be readable, at least I think so. But I will still say where the term comes from. So the term McDonald processes comes from McDonald polynomials. That they were invented by Ian McDonald in mid-80s as a common generalization of known generalizations of Schur polynomials. So Schur polynomials are classical. They go back to Cauchy, actually. Schur was the first one to use them in representation theory in 1900, roughly. And so they were previously generalized to something known as Jack polynomials that are responsible for beta ensembles, actually. They rise a certain, well, they appeared for the first time, actually, as extrapolations of integrals over Riemannian symmetric spaces that take in at beta equal 1, 2, and 4. And they are also eigenfunctions for the Calogero-Sutherland integrable system. And then the whole Littlewood polynomials, so Jack invented them, I think, in 1960, and then Hall Littlewood approximately the same time. So these are two different people, Hall and Littlewood. And Littlewood is not the most famous English Littlewood, but his student, who is supposedly not related to him. And they invented another deformation of Schur polynomials, studying the p-adic variant of the representation theory, where the parameter was actually 1 over p. So p is a prime number, and 1 over p. And then, so both families have a number of nice properties, and then McDonald came up with a way of generalizing both of them. And by now, these polynomials are actually a center point for studies in a number of subjects, in representation theory in particular. And so to these special functions, one can sort of associate probabilistic models. And the Schur processes on the bottom here, they involve the things that I started from, the tilings, and also TASEP, and the last passage percolation, and GUE. And then one can build one's way up. And so the random matrix, the beta, general beta random matrix models live here. And there is a certain algebraic formalism that comes with these special functions that allows one to compute things. And that formalism is the one that led eventually to the proof of the general beta Gaussian free field. So I'll just try to conclude now. What I've tried to show and what I've seen so far is that understanding the Gaussian fluctuations in the random matrix type models in one way or the other can be reduced to the two-dimensional Gaussian free field. It may not be visible immediately. You may be looking at a certain section of it, and the conformal structure may not be quite right. But somehow this is the underlying universal object that sits there. I tried to destroy it deliberately, actually. I tried to cook up models of plane partitions, these three-dimensional random surfaces that would, for example, have a limit shape that wouldn't be smooth, right? So there would be a point where the gradient is just discontinuous. But then, interestingly enough, well, to me anyway, the fluctuations end up being the Gaussian free field again. It's just the conformal structure had the singularity there. But that's not a problem. Once you put the correct one, you still see the Gaussian free field that somehow doesn't care about this thing. So if you know of a subtle way of destroying the Gaussian free field, then I am very curious to hear about it. One can also do things like take a random matrix, GU matrix, and add an external source. So that would split the measure into several intervals, and you wonder where is the Gaussian free field. But then if you do the multi-point extension, then what you will see is that the liquid region looks like this. And there is still a way, well, and that goes to infinity. And there is, so, if you look at the single line, you see several intervals. But then if you look at the whole picture, you're seeing just a single domain that can be, again, mapped to the upper half plane. And there is a Gaussian free field there. So this is a pretty universal object, it seems to me. Anyway, and then the extensions of that object that I tried to explain, putting the time on it, and also taking these subsequences, or taking different commutative subalgebras underneath, that gives also Gaussian processes with the covariance kernel that is easy to write, and that are universal in some sense. So from various possibilities that one can put in, they are the same. But the invariant definition of them and somehow the conceptual understanding of what these objects are is missing, and I don't have anything to suggest. Again, if you have any ideas, I'd love to hear them. That's all I wanted to say. Thank you very much for this.